So now that we've seen how things play out in this case of rod-like chromophore, let's generalize. Let's ask what happens if we have a molecule of arbitrary symmetry with up to 27 possible non-zero tensor elements. Well, now things get pretty messy pretty quickly, and I figure if you're in for a dime, you're in for a dollar. We're just going to go straight to the fully general case of arbitrary symmetry. And it's a bit of a pain because if you've got 27 non-zero tensor elements and you have 729 combinations of tensor elements, and those are all given by these terms down here on the bottom. These are the combinations of beta 2 tensor elements, all the different ways you can mix and match different beta 2 tensor elements to make things that connect back to hyper-Rayleigh scattering. And there's a mess of them. They're broken up into, this is a really beautiful paper by Berson and co-workers that we adapted this from, with some modifications with respect to the actual values in the table. But the idea is that you can take and break this product up into a bunch of different kinds of cases, and these factor of 2 and 4 just account for the fact that you have interchangeability of the right two most indices. So that's where all of those preceding coefficients come from in all of these summations. And then what do you do with them? Well, what we can do is calculate for any individual molecular symmetry, we can calculate the set of alpha, beta, gamma, and delta terms. And then once we have those, we know that, for example, chi zzz is going to be equal to 1/7 alpha plus 1/35 beta 1 plus 1/35 beta 2 on down the line. So once we know, you can think of this like a vector that we are multiplying. This is now in a matrix expression. If this was a vector sitting here, then we would multiply this matrix by this vector to generate these amplitudes. Now these amplitudes are not directly related to the intensities. We get that, let me get rid of this, by this set of expressions. This relates the four observables accessible in hyper-Rayleigh scattering to this combination of chi2 tensor elements, which we can again populate by combinations of beta 2 tensor elements. So it looks like a mess, and I can tell you that it's very easy to have a typo in this analysis that results in an error in the final analysis. An easy way to check whether or not this expression is properly operating is to rotate the molecule. Just take a triple Kronecker product of rotation matrices and rotate the molecular frame for your vectorized tensor, and then make sure that you get the exact same result for everything here. And that is a nice way of telling yourself that you're doing the math correctly. So it's a nice conformational test. So it's pretty straightforward at that point. Once you've got all of that coded in, it's a two-step operation, right? Plug in your molecular tensor, your 27 elements for the molecular tensor, Kronecker it out, calculate the alpha, beta, gamma, and delta terms, and then use those to calculate the chi2 products, and then from those, the intensities.